Okay, a quick recap of what we have done. Yesterday, we discussed about where this is coming from, and we were start thinking about some problem to solve with this. We said the governing dynamics of interacting photons in this platform is the Bose-Hubbard Hamiltonian, and then we say, okay, now we want to solve something interesting, and well, we want to solve something with it. And then the third lecture is about solving something interesting with it. For now, we just want to show something we can do that is beyond the capability of classical computers. And it was a bit of philosophical question that can we even find anything that cannot be done by classical computer? And mainly is about the scaling. Can we find a group of problems that scaling in them is exponentially harder for it to be solved on a classical computer? So it has some computer science value to it, and some school of thoughts getting affected by that, essentially. On the practical and experimental side, there are millions of dollars going into this business. Is it possible to do even a simple thing? Qubits are broken, leaky. The states leave the computational states, and they're decoherent. They're coupled to environment, and lots of challenges in any platform that you can imagine. So is there anything we can do? We mentioned that there is a well-defined problem. I get to it, which if you look from a more abstract way, there has to satisfy this criteria. But the problem we chose indeed do satisfy the criteria that is commonly required to be satisfying. Mainly, we start with one wave function, which is a pure wave function, is a product state, is simple. We can prepare it with high fidelity. And then there's a sequence of gates that we can tell you what they are. There is an entangling gates. There is a single qubit rotations. And the claim is the wave function evolves according to this. And then you can sample from this output wave function. And it's very hard for a classical computer to know, predict, put bit string as good and as fast as a quantum processor can do. Vazirani's team in 2019 showed that this problem is sharply hard. I don't know what it means. It's hard. But also, yeah, please ask question anytime you like. I ask Esther to stay back there to hand you microphone if you want. The first thing in this business is to show fidelity of the operations. And that's a very crucial thing. This is very big message I'm trying to convey in here. If these integrated histograms are a little to the right, meaning the qubits are more faulty, the computation gets substantially simplified, and we could not make a case. So it's important to know that single qubit gates are about 3 nines, and 2 qubit gates about 2 nines, and readout was the dominant error and is about 3–4%. In fact, at the end, I show that the recent work by the Chinese team outperformed us just by making these results better. The coloring, so this is a grid of qubits. The color we chose for on each qubit. If you could get this light off, is that possible? It was off yesterday. There you go. Yeah. So the color of the qubits is representing the error that you're seeing in here. That's the choice of the color. And the coupling is represented, oh, perfect, by those squares. And the color of it is chosen to show the error. So there's some rather uniform distribution of errors with these histograms that you're seeing. So the first two messages that we want to discuss and show you experimentally how we do, there are two main pillars of the business is complexity and fidelity. The problem is complex, and I try to show you experimentally how we go after that. And the problem, and we have control over fidelity, and we have a metric of fidelity on how to measure things are working. And this is an analogy to classical physics that you might know. The notion of complexity we are going to use, we're not going to show on the spot what is complex, but at least we are going to show that the entire Hilbert space of 2 to the 53 is effectively or practically is in use. So we have evidences for that. And here's where the evidence comes from. Let's say you get 6 qubits, 9 qubits, or 12 qubits, and you do the dynamic I just described, the sequence of single qubit gates and 2 qubit gates. And these are small Hilbert spaces, so you can repeat the measurement, I don't know, maybe 250,000 or 1,000,000 times, and then you can see what bit strings I get. So this is the bit strings, how many times I get a given bit string, how many times I get 000, 001, and so forth. So this is showing you how many times you get this bit string for a given unitary operation for a given random circuit that we have chosen. And you can see that you can do this up to 12 qubits, 15 qubits, but after that you realize it's just, you take many more data to arrive at probabilities. You look at the vertical axis, so here you could get in order of 1,000 in most cases, most typical cases, and here you can only get a few times. So the next thing I'm going to do is I'm going to take the most probable bit string, forget what would actually correspond to, put it to the left, and put the least probable bit strings to the right. It's just sorting them, nothing fancy. It's the same data, I'm just moving things around. Now, the complexity argument we are going to use is that this distribution have a particular shape, meaning is an exponential. And that is the reason that we are thinking, because it's exponential, it's indicative of the fact that it uniformly explores this available Hilbert space. Here's the line of the argument. It's not necessary and sufficient, but that's the best we can do given experimental things. Well, you have a wave function. The wave function can be written in this computational basis as a bunch of complex coefficients and a bit string, right? These complex coefficients can be written as real and imaginary part. And uniform exploration of Hilbert space, there is a theorem tells you that implies if and only if these parameters, the real parts, obey Gaussian distribution. And if they obey Gaussian distribution, they're random variables, essentially what I mean. Then C1 dagger, then they would obey the exponential distribution. And that is the, well, but note that this, the last arrow is one-sided, so it's not really, it's not proof. There are other systems which show that, but we are going to assume or just, that's the best we can do. That, you know, we're going to, the fact that this is exponential is provide a strong evidence that, that we are really uniformly exploring the Hilbert space. And this can be done up to 12 qubits, 15 qubits. Beyond that, you just cannot get probabilities, and we have to think harder of what we want to do. So I leave the evidence for uniform exploring the available Hilbert space in here. And we are going to get to the notion of fidelity. So here, the experiment done with a slightly different pulse sequence on a small setting. You get a bit string, and here again the probabilities of bit strings, and then you know the Hamiltonian you have. You can exponentiate the Hamiltonian, or you know the unitary eventually, and you say, what did I expect to get, and what did I get? And the points over there, that bar thing is what you meant to get, and some standard, okay, maybe it's missing, I don't know. Anyways, the signature of this looks like a speckle pattern, so I'm trying to connect to that boson sampling example I said that kind of inspired these experiments, is that in boson sampling we discussed, you have photons coming into interferometer, and these photon quantum degrees of freedom, they interact with, they interfere with each other. Here, you can essentially imagine the hardness of the problem is that you have a product state, and this product state become highly entangled state as a result of the interference, if you want to think about it this way. And it's very similar to this laser speckle pattern. You know, you have a coherent wave coming, and these parts of it is interfering with each other as they go through the media, and you don't get a Gaussian distribution as you get with this decoherent source of light, but with the laser, if you would get some very detailed speckle pattern, and this speckle pattern is really the signature of the media that the wave has traveled through, and we would compare exact with approximate, the exact number you know from your classical computer with what you get in the lab, and that's the notion of fidelity. So it's a very simple notion of fidelity, meaning that this is just the entropy. You compare Pi is the probability of getting a bit string in the lab, and Qi is the probability of that bit string coming from your classical computer. You compare them, and the rest are just a bunch of normalization and whatnot to take care of the random chances, right? If you just flip a coin and write down the bit strings, you have to be sure in that case you get 0 fidelity. So you renormalize your fidelity, and that is the definition, but the essence of it is just P log Q. Or you could use P dot Q or Q log P. All of them would work more or less equally. So it's just the notion of two distributions being very close to each other gives us fidelity. So you can see for up to 9 qubits, as you go deeper and deeper, your fidelity exponentially coming down. And we have a good hold of it per unit of qubit, per cycle, how much error you have. And that has to kind of stay up to a good degree for us to be able to claim we can outperform a classical computer. So this is the fidelity metric we are going to use. And now the most important question is, OK, how are you going to go to a very large system which you really cannot do compute? How would you put fidelity there? If you could know the fidelity, mean that you could have done simulated on a classical computer. And if you could have simulated, then what are you claiming? That's the challenge. Well, luckily, something we discovered more or less maybe by accident is that, again, computational complexity is a very fragile function of the order of the gates that we are applying. You can apply a sequence of, so when you have a 2D grid and a qubit cannot be involved in two entangling gate at the same time. So you have to decide which way you want to apply your gates. So if you apply E type of gates first, and then F and G and H, so you have done it correctly. A qubit has talked to its north, south, east, and west. And now you want to repeat it again. Well, you have two options. You can repeat the sequence again, and you can not repeat exactly. You can do A, B, C, D. You can do C, D, A, B, right? The next time, so there is it takes 8 actions to come back to where you started, right? Here, it takes only 4 actions to come back to your start, right? You have this degree of choice that how do you start your second sequence, or you want to do it uniquely, different from the first or whatnot. It happened that if you do this one, which is what we did before someone caught it very last minute, this can be really simplified in terms of computation. Lots of contraction in the matrices that are leading to the computation can be done and can be simplified. So we would embarrass ourselves with claim supremacy over this. But we realize a simple modification of the sequence makes it, as far as we know, really bulletproof, and then we can make the claim. So, but when you think about the quantum processor, the gates are faulty to a degree, and you're going to assume that it really doesn't matter which way you order them. The errors you're just going to accumulate is extremely unlikely to think that this would have more errors than this one, right? It's just a little different. I mean, you got to believe me. There is no evidence for it because you cannot do this computation. But you think in terms of fidelity, at least you can just do these simple things, have the same number of gates, only applied slightly different in time, and you're going to assume that's inconsequential in terms of fidelity, so we are OK. OK, so on the right, on the left is something we can compute. So I would show you we can have fidelity. On the right is going to be the claim. As I mentioned, this is the simple notion of fidelity that we are going to use, just based on notion of entropy and measuring the distance between two distributions. But we have a problem in here. Here, there are two probabilities. It assumes in the lab we could measure a bit string enough time to know the probability of its occurrence. But when you have 10 million billion dimensional Hilbert space, and you can measure maybe a million bit string in a few minutes, there is no way for measuring much more than the size of the Hilbert space to be able to arrive at probabilities. You get a bit string once, and you're not even that lucky to see that bit string twice. 2 to the 53 is much more bigger number than the number of the time we can try to arrive at probabilities. So there's a question? No? We good? So we have to play with the whatever we want to do for fidelity. So let's say you get a bit string xi, and this bit string xi is not going to repeat itself. Nevertheless, you have to know the probability of that bit string from your classical computer, and then you average over the number of times this happened, over the bit strings that you measure. You get some bit string, you say, oh, that was its probability. You just write it down, this probability score, and then you do it over all the bit string. You average over all these probability scores, and the rest are just a bunch of normalization. Again, to be sure, flipping of a coin and just writing bit strings by chance is going to give you exactly 0, right? Pxi average would be 1 over 2 to the n, and then you see normalization gives you exactly 0. So that's the notion of fidelity you see on the vertical axis. On the horizontal axis, we are going to play with number of qubits or number of cycles. And these are the two patterns that I was talking about. So here is rather simple. You do these gates, and the second time, you do these two first, and then A and B, and that happened to be simple. Yeah, and this is a warm-up case, meaning that we killed every gate that connects the left side of the chip and the right side of the chip. You have 27 and 26 qubit chip essentially parallel to each other. There's no entangling gate between, so you have two systems. It just happen to be next to each other. So 27 qubit and 26 qubit experiment, we can simulate in a classical computer. So you can see the fidelity coming down, and you have all the numbers you want. Okay. The next is we are going to remove the gates that connect the left side and the right side of the chip. But the way we are going to do it is we are going to remove it maybe only for a couple of cycles. And then, let's say from the cycle 4 or 5th forward, we are going to connect them together again. So that's called elided. The first initial few cycles, the left and right are really not talking to each other. The gates that were connecting across them, in here, I think that they were not used to make the computation simpler. So if you the point is that there are about 1,400 gates applied in here, and if you kill 50 of them, and you know which one to kill and what time to kill, the computation gets substantially simpler. While you can believe that removing 50 gates out of the sequence of 1,400 gates is really inconsequential. That's the thinking there. And now comes the real deal. You don't remove any gates. And on the on the left, we can compute it because, as I said, this is the sequence of gate is in a given order, and we can give a time, and up to here it would take 5 hours or so. However, on the right, we are going to just say that how long it would take for us to do this, and this is the time it would take to simulate the wave function. But you might say, wait a minute, your fidelity is really, what is it? 10 to the minus 3. It's crudely speaking, roughly speaking, 1 out of every 1,000 bit string is correct. I mean, everything is probable, so there's no right and wrong. But most of the bit strings we are getting is wrong. Only 1 out of 1,000 is good. Is not error, is fidelity, which is close, that small. Yet again, problem is hard. So the fidelity is very low, and we are saying it takes that much time to simulate it. This is unfair to classical computer. We have to take it easy on a classical computer. You say, well, you can also put bit strings out which are as wrong as what we do. After that simplification, then we can put a timestamp saying that at the given fidelity, it is a productive factor. It doesn't enter the exponential. So it's just this computation, this number gets just divided by that factor. That after that, it would take 10,000 years to create bit strings at 53 qubits at depth 20. So it rests on us wanting you to believe the fidelity is here, given that it's only different from the other case by just simple reshuffling of the gates. Yes?
Yeah, maybe I missed it, but you said that the two are the same, right? Up to changing of order.
Yes, yes.
Why
Yeah.
is there then such a big difference in fidelity between the two graphs?
There's none.
No?
Where is, so you go 14. Yeah, there is likely
the
difference.
number of cycles, it's 12 cycles, 12 cycles on the right graph. If I compare that to 12 on the left.
No, but on the left is number of qubits, the right is number of cycles. So the left one is all 14 cycles.
Thanks.
And also the sequence, well, yeah, but there are differences too. There might be different unitary or something too. Yeah, but it's not that different.
The point at the 14 is comparable at the other side. So
There you go. There was one more? No? We good? We made the claim. Okay. One big take-home message of this experiment, which is very important message for the error correction community, is that we could have predicted the fidelity by just making the product of the errors of the individual pieces. The total error is nothing but the product of the summation of the errors, and there's no extra new errors is born after we do all our local calibration. So the solid line, black line you see in here is nothing but just knowing the product of the individual errors that I was showing a histogram of it in a few slides earlier, and you just product them, and it really predicts the fidelity of the system as it comes from the full quantum simulation at the same time. So it's a very important message that there is no weird errors going through your system, so it gives some chance for error correction ideas to actually work because they are dealing with large number of physical qubits to arrive at a logical qubit. Okay? So that's a very important message. So let's get into how we do this computation, where the computation come from, would you do that? The most naive approach that I would be taking and would be very happy to is just to write down the Schrödinger equation and just simulate it. You have a wave function, big wave function, and you just evolve it in time. And the problem, so here's the color is the time it takes to simulate just something I would do in my laptop with number of qubits and a number of cycles, and you can see that in time it doesn't get much harder, you know. So 30 qubits in a laptop, let's say about 30 qubits at depth 10 can be done in a minute, but then going this way, getting more and more qubits, the time goes up faster. However, these lines, the time is not really sensitive function of the depth of the circuit. Meaning that you look up there, I'm showing you the memory requirement, and that's really the key concept in here. This computation is not that time-consuming. It just needs a large number of memory. So here you can fit up to here, laptop, 30 qubit you can fit in your laptop or the laptop we considered. And Jülich is the supercomputer in Germany offer you that much memory. This has to be done in RAM. This is not a, I was explained this to me several times. It cannot just do in a hard drive. We get into that too. And this is the line that the Summit supercomputer at Oak Ridge National Lab has, meaning that 50 qubits is just beyond the wave function, just does not fit in the RAM. Okay? So in this planet that we live in, it's not possible to do this beyond 50 qubits with this approach. Some of our colleagues live in a different planet. They think they just keep going. It doesn't take that much time. We understand that. It takes a day. But it maybe in parallel universes, there are things that could change it. But here, there's no enough memory in any computer anyone made to fit the wave function with this approach. So what did we do, or what is customary to be done, is inspired by this notion of elided and whatnot. It's just the notion of Feynman path integral that you say, OK, look, I do left and right, and then I see how many ways left can talk to right. When you do left and right, so you really substantially bring your memory requirement. You have too much smaller system. But there are exponential number of ways that the left and right could talk. So you can stitch them back together of all possible ways that they could have communicated during different stages. So you're trading off a space and for time. So the time is now going to be more sensitive and it's going to blow up. But it's just going to easily fit into memories. Now, 1 petabyte, it comes very accessible. 1 petabyte, which is right at the limit of Summit, it's on the left of it, is now, can take you up to some 50 number of qubits. So this is the essence of the computation that we have done. Not doing simple Schrodinger, which is fast, but it doesn't take you to that many qubits, but really coming to trading off space. So that the next level of question is, well, how about splitting into 4 pieces and connecting them? That's a very good idea, and that's really the essence of what people would do to outperform our thing by figuring out how to play between a space and time requirement. What is this? Oh, this is about error I mentioned. As I said, the error gets is a key concept. If the gate's fidelity were much smaller or by factor of 2 or something, then the computation, if the errors were higher, sorry, the computation would get substantially simpler. And that's the point of this plot. The difference, maybe it's hard to figure out what is the difference. This is more or less, well, we are somewhere in between, so I didn't want to show the same thing again. If the errors is very low, there is a chances that you get red regions. But if errors are 2% or 3%, forget about it. If you have 3% error, which is 3 times what we got, let's say everything is dominated by 2-qubit entangling gate, there would have been any claim of supremacy. So if you have 3% error gate at home, don't try the experiment. It's not going to work. OK. The next thing to show, to relieve shadows of doubt from your mind, is the notion of chaoticity, or again, along the line of sensitivity to choice of gate. You might think somehow that, nothing mattered, it's just going to work out. This ergodic behavior, how are they really sensitive in choices of gates? I think what I want to show in here is that indeed the whole computation is very sensitive to choice of gates. This is the first quantum instance. Let's start with a classical instance of sensitivity choices. Antonio Salieri was a rival to Amadeus Mozart, so he really hated him. Nevertheless, he had to confess that if you get a Mozart composition and change a single note, it really what is his word? Diminishment displays one phrase in his notes. So he had to confess to it. So we, inspired by this historic event, we just say, what if we just change one gate? It was a square root of x. Let me just do it the square root of y. You can do it in the lab, or you can fool your computer and say, what if this was a square root of y? Ask your computer to do it differently. As soon as you make this tiny change in this whole sequence of gates, one single qubit gate is changing, you would see that the fidelity drops by 2 orders of magnitude. Well, Salieri failed to quantify how many order of magnitude that fails, but here at least we are doing is saying that, look, it really falls by 2 orders of magnitude. So it's really the notion of chaos in the quantum system, right? We talk about ergodicity, meaning uniform exploring Hilbert space. Now I'm showing sensitivity to Hamiltonian, right? I have a unitary only. But we are showing that how sensitive it is to the choice of gate. So this is hopefully you appreciating that what we do actually matters is not that the strings come for free and you could just flip a coin and get them. So let me summarize this experiment. And it's important to summarize it because it gives you the notion of where we are in terms of NISQ algorithms, right? This experiment is considered as as the moment that we are now trying to maybe do things with quantum processors without error correction. Is there a hope to solve something with? And these numbers are giving you a place where we are in the phase space of parameters available. And so if you have your favorite problem maps into millions of gates or so, you can see it's really beyond our capability. So this is saying that the ballpark of where the discovery could be, in fact, the upper bound of where it could be, because most problems have a structure, and it takes much more to beat a classical computer on structured problems. So 53 qubits, going depth 20, and the total number of gates about 1,500. And this is the fidelity, and also extrapolated fidelity is important. So let me end it in some philosophical thing for the computer scientist. It's really, in some sense, is analogous to Bell test of early 1980s of Alan Aspey and his colleagues, where they really ruled out the possibility of local hidden variables, right? Well, at least that's a common interpretation of these days. Here we are showing that there is the quantum is really capable of doing a computation beyond what our conventional way of Church-Turing model is. So there is a Church-Turing model thesis which says anything for anything that can be an algorithm, this algorithm can be done on a classical computer or can be done on a Church-Turing machine. Then there's an extended notion of the Church-Turing machine, which is extended thesis. So the extended thesis is concerned with efficiency of such a calculation. Say, yes, you can map it, but is it polynomial in resources? Can it be done efficiently? And now we are saying, and well, the claim is that, yes, it can be done efficiently. And now we are really challenging this extended thesis and say that, no, there are computations that cannot be done efficiently. Yet nature is kind enough that provides a computational tool for you so you can do it efficiently by using nature itself. OK. And our work, we like to think it this way, our work really inspired many people to try to outperform us. And this really led to lots of activity in computer simulations of the work, and we really, really welcome this. So this is where we claim what we claim, 10,000 years. And you can see it really comes down to 15 hours after several works of other people. And it's really, we really welcome this understanding that developed this. But again, we are not the record holders of quantum supremacy anymore, but also it's a philosophy, is a way of thinking. We have said it in our manuscript here. We expect that this cost of simulation would go lower. It's not a, well, it's one thing is about who has the record, so sure, but it's also about one being polynomial, one being exponential. That doesn't change. And that is really what we have said, that, yeah, sure, it's going to change, but the physics is the same. OK, so what is the thinking behind this that leads to this advancement is the way they think about this evolution is they think about tensors and how to contract tensors. In one dimension, maybe there's not much to think about how to contract these tensor networks. But when you come to 2D and you look at your gate sequence, then there's lots of ways to think about which one to contract first and which one to contract second. And that's what goes into these games that leads to this advancement. And that really the tensor network method is really the working horse for all this effort. OK, questions? OK, perfect. So I want to talk topology, so you guys feel it was justified to invite me. And then there would be a NISC discovery experiment for the afternoon. So here is the team of the people who did the project, which probably closer to your heart, something on topology. So I want to prove myself. Or use the word topology at least a couple of times. So the work is really done by the infrastructure of the Google. This is representing maybe 120 people or so. But these colleagues of mine were more seriously involved with the work and spent time on it. The work is done in collaboration with Frank Pullman and Michael Knapp's team, and our chair was part of the this effort. So the idea is to synthesize the ground state of the toric code model in the lab. The toric code model of Kitaev is exactly solvable model and is a Hamiltonian written for the surface code purposes, or the originated of the surface code, in fact. It was written in torus, and then people open it up on a 2D plane and whatnot. Is a Hamiltonian. We cannot realize this Hamiltonian. We cannot realize the phase. We don't have bath. We don't have the phase, but we can synthesize this state associated the ground state of this system. And this state's going to be there, and it's going to decay into nothingness. But the idea is that we can come up with a sequence and just arrive at this, and then study the property of this state. So why that's interesting? Well, in terms of design and what Adam and his colleagues thought about, it's a problem with long-range pattern of interaction. And then how can we sufficiently fast and few number of gates you can get to really synthesize something with this? So that was the theory challenge for Adam and his colleagues. And for us was another way in parallel to effort of realizing these phases in condensed matter system to see if you really realize these phases in a solid state systems, what are the challenges, how long they're going to last, and what can you learn, and all these complications that a solid state experimentalist would face. So this is a Hamiltonian defined on a square lattice, which says every time you see a qubit, you have to get product of 4 x's. This is one term of the Hamiltonian, sum over all possible plaquettes, and then there is sum over all possible vortices. So qubits would be located in these bonds, middle of the edges. And here I'm showing you the final result of measurement. Let me show you how we got there. So we have a grid of 30 qubits, 31 qubits, which takes to realize this pattern. And every square in here is a qubit. And with a sequence of gates, which is extremely efficient, is just actually the number of layers that in the protocol is linear on one side of the system. So you have a n by m grid of qubits. It just takes n or m layer of gates to arrive at this ground state. So you put certain qubits on the equator, and then you start an entangling gate and try to essentially propagate the entanglement from the center of the chip to the side, and after a couple of steps, you arrive at this ground state. So the color here is showing measuring these stabilizers of the code. You go and say, what is the expectation value of XXXX and ZZZZ, and that's what the colors represent. Am I making sense? So we realize the state. The state is in a large Hilbert space, but at least we just measure very few numbers of it just to show that we know what we are doing. So, well, the whole thing is rooted in the fact to realize that what the ground state is. The ground state, because all the terms in the Hamiltonian commute with each other, the ground state takes a really simple form. So you know it, then you go and reverse engineer the gate sequence that could lead to it, and that is where this is coming from. And here I'm showing you the evolution. This is what I said. The scaling is really favorable. Is really linear in the dimension of the one dimension of the system. So it's not a hard job to arrive at it. And here you can see maybe certain measurement of these stabilizers as how they evolve as you get toward realizing it. So this is a half-cooked wave function, and eventually you get there, and we are trying to show that, in fact, indeed is made of equal superposition of all the possible configurations. I'm showing it here for a smaller case. Full disclosure of data. This is a small system, so we can really do readout corrections, and we can measure a probability and say what are the chances that this probability gets skewed because our measurement scheme, as you remember, was the faultiest thing of all, could turn 0 into 1 and 1 into 0. So there's a scheme to correct for it. It's just linear algebra. And that's what we have done to arrive at the numbers you see. So originally it didn't look as glorious as you're seeing it. Okay, so let me try to prove membership in the club by showing something about topological phases. So first thing we said about try to explore about this state is to measure topological entanglement entropy. So, and this number is what we are trying to measure. It may, as is indicative of the fact that you have entered the phase. So let me tell you what it is. You have a bunch of qubits. You can measure how pure they are, how this subset of qubits pure they are, how entangled they are. And when you're looking at this entanglement with surrounding qubits, has two contributions. One is the boring one, is just coming from the dynamic. Another is this topological and universal one. This relation, which says that measure entanglement entropy of qubit subsystem A with its surrounding, and then subsystem B and C, and then subtract this, and then add all this together, is made to remove the edge contribution and to leave you with only the topological entanglement entropy as a pure number. So this is, if you go through this, when you're measuring S of A, you're getting contribution from 3 edges of A. And then when you're starting subtracting AB, then you're removing this edge contribution. So you have to, this is one of the simplest construct, which allows you to remove the edge contributions and give you at a universal topological entanglement entropy. So longest story short, in the lab, you have to make here all these single individual islands, this subgroup of qubits, and you put it together. So we have done it on a group of 4 qubits, a group of 6 qubits, and a group of 9 qubits. You divide it into subgroups, you go read the entanglement entropy of them, and then you just add them up. The beautiful fact about solvable models is you know what you got to get at the end of the day. And it's very simple. You have a group of 2 qubits. Its entanglement entropy is really related to how many edges it crosses. So it's a very simple geometric, the edge contribution. The whole entropy of a subsystem is really simply given by essentially how many darkened square this crosses. So you just draw a line around it, and you just count the number of things, and you just know what you're going to get. This log of 2 is there to make peace between condensed matter people and computer scientists. I don't know which one want it, which one doesn't want it. It's very strange to me, but that was one way to make peace between them. Here's the experimental results. Let's just focus on the top row. Here we are talking about this 2x2 system. And when you look at the A subsystem is a subsystem of sorry, what happened? Is a subsystem of 1 qubit. Okay, sorry, this one is here, right? When you look at the entanglement entropy of one subsystem, it reaches to be 1. And when you get to 2, it reaches to be, so it means it's maximally entangled with its surrounding. 2, you get 2, and 3, either configuration, you get 3. And when you know the entanglement of these subgroup of qubits, you can put them in this formula, and you can get this total entanglement entropy. Which, yes, please.
So you're measuring a Renyi entropy?
We are measuring a trace of rho squared. We do full tomography, and then we get.
So you make 2 copies in order to measure trace
No,
of
no.
rho squared?
They want you to hold the mic. I get to it. For small subsystems, we measure all Pauli. Let's say we have interested in subgroup of qubits A, made of 3 qubits. We measure all Pauli bit strings, and we construct a density matrix. From density matrix, we get trace of rho squared. And this ran into problem when the system is large, and I get to that.
Thank you.
So here is simple. You have number of qubits n, you get n, because there is no notion of interior. You have 5 qubits, is maximally entangled, your entanglement entropy is 3. As soon as you get, so now let's go to this 2x3, and as soon as you get to 4 is right. So as soon as you can form two distinct geometries, so you have 4 qubits here, and his entanglement entropy is 3. So you see at 4 qubits, and his entanglement entropy is 3. And you have 6 qubits as his entanglement entropy meant to be 4. It comes from this geometric argument. So again, you go and do the measurement, and you put the collected numbers together, and you get the entanglement entropy with certain errors. The distribution of errors come from the fact that this patch of 6 qubits can be many different configurations, can be many different places in the system, right? And now it starts getting interesting. When you get to 9, that was our challenge. And then really the geometry starts to matter. Now you can have notion of interior, closed loop, and whatnot. And really, things are less boring. So here again, up to 3 is boring. You get entropy of 3. 6, you get 4. But then up to 5 and 6, then you really depend what is the shape of this subgroup of qubits. And you get the entropies, and you put together, and you get 95. But the theoretical prediction is that this has to come to -1. So what is a big deal in here for us experimentalists was that you cannot do what I just explained for 9 qubits. So you might wonder how we got to how do you get the density matrix for 9 qubits to get that purity? The fact is we did not. We rely on cleverness of Peter Zoller and his team to tell us how to do it. So it happened that you have enough bit strings randomized, measured in a randomized basis. Then you can really look at the correlation at bit strings and approximate this second-order Rene entropy from this formula. So up to few number of qubits, tomography is the way to go. 5 qubits could take you maybe, I don't know, 20 minutes. 6 qubits, a few hours, and then 7 qubit is a big no. You cannot hug the system for 3 months to just get a single number out of it. But the correlation in the bit strings that you measure, so you evolve unitary, and then you put a sequence of random gates at the end to scramble your states, and the correlation you see in that bit string as captured in this relation, it's good to approximate the second-order Rene entropy. And that is the trick we use for getting this single point in here, the 9 qubits, this histogram distribution for it. It by itself was a big deal, just to essentially extend the notion of entropy or measurement of entropy to a subsystem of 9 qubits. So you can measure everything up to this SABC, this subset, which we know from theory has to be 5 is entropy, but it took many efforts to get there. Am I making sense? Good. Okay. Let's see. What we could do, okay, so you guys are into abelian and non-abelian particles. Let me also talk a little on that, then I take questions. The excitations on top of this ground state of this system has abelian statistics, and so we can create them simply as soon as you synthesize the ground state by applying a pi pulse or a z pulse. You can create them, and you create a pair of E particles or pair of M particles, as you guys call them. These are some historic naming. So when you go back and you measure your stabilizers, now you can see that 2 of them are showing exactly opposite value than the ground state. And we call them, you can think about them as quasi-particle excitations on top of your ground state. And you can get an E particle. They come in pairs, so or if well, okay, something. The notion of edge and boundary become very important. So you can fool the system by actually not creating a pair, and you can really create single one of them. So if you see single one of them, don't be alarmed, because it just came from the given where corner you bring it in. The pair of it could be on the other side of the boundary. It doesn't exist. But as soon as you create an M, you can use the same sequence of pulse to get this M to circulate around E. So I'm doing a braiding. These are semions, I guess, and you're going to get a minus sign. So I'm demonstrating it. Now the wave function accumulates a minus sign, but good luck detecting it. There's nothing detectable there. The wave function now is get a global minus sign. To detect the phase accumulated, you got to be slightly more clever. I couldn't afford it, so Kevin did this part. So you have a wave function in the accumulated global phase. There's no way to measure it. However, if you conditionally couple your unitary evolution to an ancillary qubit, to an auxiliary qubit standing there, and you put that qubit on equator, the auxiliary one, the rotation in the angle of that qubit is a simple thing to do. You can do it yourself. I insisted of having it here so people can see how simple it is. This qubit, which was in 0 plus 1, is now going to go 0 plus e to the I theta 1. And that theta is exactly the phase, global phase accumulated of that system by this interferometry, or however you like to call it, thanks to ancillary, become a detectable phase. So now what now I can do, well, maybe this picture help you, maybe it doesn't. So now I can braid anything around anything I like, and I arrive at the full, what do you guys call it? S and T matrices, essentially. We can see what happens if we bring E around M and M around E, and then make an E and M go around another one, right? E and M form a composite particle called fermion. So we can arrive at this full table of abelian statistics of this particle. Mainly you get 0 or you get pi phases. So we are showing that we can do this kind of manipulation, which is essentially the essence of how to make gates with these. Well, you need the non-abelian version to begin with. Also, is there a question? We have 3 minutes. I can explain this or I can take questions. Yeah, please.
I wanted to ask, do you have a fidelity as a function of the size of the system, at least for sufficiently small systems?
This is kind of talk about the notion of fidelity.
Oh, okay.
Yeah, maybe, okay. Is there more I can answer?
No, I wanted to ask that one. And also, when you show the error bars for the braiding of onions, so
would this give you a sense for it? Okay. Well, yeah, this would give you, I don't have exactly that, but this gives you a, let me see if I can have, well, maybe the fact that these numbers are not exactly 0 give you a notion of fidelity. And these numbers are not exactly pi give you a notion of how bad we are.
And the fact that the fermion has a almost double error bar is because it's like this compound. It's because of some experimental factor?
Yeah, the gate sequence get larger. So you see, we are showing before and after, and these nominally have to be identical. I don't know if you get enough contrast in this screen, but they're meant to be identical, but you see they're more pale because you do this and you accumulate a phase as a global phase, but this wave function is not really changing in terms of these local observables, so it should be identical. But it's not, and you can see things are losing color, losing contrast, and that's exactly because of the error you're interested in.
Okay.
Yeah.
Thanks a lot.
Yes, Jason.
The toric code's an abelian topological phase, but it has non-abelian lattice dislocation defects. I wonder if you guys have explored that.
Yes, but yeah, we can talk. Yeah. We are thinking about that, yes. Okay, but maybe I also go and briefly show this. So the whole business is about to make a logical qubit. Let's see how logical qubits look like. And the idea is that here is 3, 3, 5 by 5. This is most likely interests you because we're going to go bigger and bigger and see is bigger get better. And the short answer is no, unless you really do active error correction or proper error correction, or at least we are close to threshold, enough close that just making it bigger, it doesn't fix everything you like. So the sequence was simple. We don't have to get to the ground state. So you can imagine I can also make all possible points on a logical block sphere. The algorithm I'm not showing you here is similar to gate sequence we made. You know where you want to get into, so you come up with a gate sequence for it. Doing it in a scalable way is a big deal. We don't have it, so I'm just showing you the final results of a gate sequence that led to these logical measurements. But also we can say how good they are. You know, I make a logical X and I just watch it as a function of time and how fine it's going to, how long it's going to survive. So it's just wait time. You know, it's like a T1 decoherence of a qubit, a logical qubit that you just keep watching without doing much action, or T2, the Ramsey dephasing of a qubit. The top panel associated with this 3 by 3 and the lower one was 5 by 5. This is there's no measure qubit, data qubit. This is a very crude way of doing things. There's no, there's not that distinction. So what we do, we measure this logical X or logical Z, let's say, and then we come and see if we can fix for them. You have measured across the entire grid, so there are cases that you see if something flipped and you can flip it back. You know, it is post-processing. You look at your bit string, see how fixable it is given simple arguments. And at some point, it's not become fixable. And that is the errors that you are seeing in here. As a function of time, the error grows. So you get rows of, let's say, you make a plus logical state, 0 plus 1 logical state, or you make logical 1 state, and they are just rapidly decaying. With this post-processing error correction scheme, you can come and make them better, and they come down in here. Well, it gets better, and then if you pay attention to the fact that you could have decoupled, you do some dynamical decoupling and whatnot, that's this extra step that we took. So we can forget about that detail. But from this raw data, which decays very fast, here and here, you can come down, correct them, and bring it down to here. So error correction can help you to remove certain errors. It doesn't fix everything, and you may wonder if 3 or 5 better than 3, and you can see necessarily not. So we are in this experiment, although later we improved it. In this experiment, you see we are sufficiently close to threshold that there is not much point of going to larger scales, and we needed to work harder on the hardware. So that's how these toric codes essentially correct to logical states you want to make in the lab, and I think that's a very natural point to stop.